Sounds good. All right, cool. I guess we'll get started now. So on Wednesday we covered the first 7 topics. Now we'll go through, I guess, 8 through 11. And 8 and 9 will be me, and then 10 and 11 will be Yolanda presenting. Cool. So I guess the point of topic 8 is, we have some function. For simplicity, say it's just a function from an interval to the real numbers. And we want to integrate it, but we can't find an explicit expression for the integral, because integration is difficult usually. And so we want to sort of pick some rule for estimating this integral along this interval. And I guess the naive thing to do is sort of just a Riemann sum, if you remember from Math 1A 1B, where you sort of cut the interval up into equal slices and then sample the function at one point in each slice and sort of take a sum and weight it by the length of each slice. And that's sort of approximating the average integral over that little section of the whole interval. So I guess that's sort of similar to this first rule here, which is just the midpoint rule. And basically we're cutting our interval up into x0 to x1, x1 to x2, and so on. And then we're just going to sample the function at the midpoint of each of those subintervals. And then we're going to multiply it by the length of the subinterval, and that sort of gives us an estimate of the integral over the subinterval, because we're sort of assuming that the function across the whole subinterval is equal to the function at the midpoint. That's the approximation we're making. And then we're just going to sum that up across all the intervals, and hopefully that gives us an approximation to the integral. I guess that's a reasonably good approximation. We can sort of be more efficient if we sample in a slightly different way. And there are a few different choices for how to do this, but two that work well in practice are trapezoidal rule and Simpson's rule. Trapezoidal rule, rather than sampling at the midpoint of the interval, we sample at the ends of the interval, and we sort of take the average of those two values. And you can think about this as sort of, if we sample at the endpoints of the interval, we're saying that the function height at one end is some height, and at the other end is a different height. And then I guess you can approximate the integral of the function over the interval as saying that, well, if you graph the function and you look at the area under the graph on the interval, that looks approximately like a trapezoid if you assume that the function is roughly linear. And so I guess the reason of the trapezoidal rule is because you're sort of assuming that you have this rectangle shape with sort of a triangle cut out of the top, and you just use the area formula for trapezoid to compute the area of the approximating shape for the subinterval. Simpson's rule doesn't really have a comparable intuition as far as I know, but it's doing the same sort of thing of just looking at, you have some difference term in terms of the x's, and then some weighted sum of different function values, and you sum that up over all of the different intervals. And I think this should be n-1 here up in the top. And that's just to account for this I+1. Cool. Yeah, so these are they're just formulas to remember, I guess. And Simpson's rule generally does the best. I guess you can imagine that it would do the best because it's the most complicated. And no reason to make it complicated unless it's better. So this is roughly in order of complexity and also accuracy or efficiency in terms of samples. Yeah, so I guess one concrete example of quadrature, and this is using a different method to the previous three, which is Gauss-Legendre. I don't think we actually need to know the specific weights and the specific function values for Gauss-Legendre, but yeah, basically the sample answers for this 2014, which I think were not written by the course admins, they were written by someone who took the course in 2014. But yeah, the sample solutions just put it in terms of this weight and the function value. And I guess the slight complexity arising here is that Gauss-Legendre is taking, I guess you would compare it to the x values. It's taking its function inputs from this interval -1 to 1, and we actually want it to be 0 to t. So I guess that's why there's this little transformation here of the nodes at which the function is sampled to solve the quadrature problem. But yeah, I guess other than that, this is just the general idea of quadrature is you have the weights representing the width of the interval, and then the values at which to sample the function, which in this case is just r. And we use that to estimate an integral. And I guess the more points you have, the better the estimate you would expect to get. But obviously the more expensive it gets to compute that. Yeah, so that's the basic idea of quadrature. I guess this one is a little bit scary. It doesn't seem to come up a huge amount in the exams, but it does come up in some questions. So yeah, I guess there's a lot of different symbols on the page here. But to simplify it a little bit, I guess the general idea here is going back to these quadrature rules. These were all for a function taking a one-dimensional input and giving a real number as output. And so we have all these rules to compute a function like that. Now we're looking at the case where we have a multi-dimensional input to the function. So that's just going to be a vector in this, I guess, unit cube in d dimensions, rather than the unit interval in one dimension. So that's where this x vector is coming from. And I guess the idea is that this is sort of a bunch of nested integrations. And because it's a bunch of nested integrations, well, when you have a nested integration, you're basically, the innermost integration is a function of the variables that the outer integrations are integrating with respect to. Yes, I'm not quite sure how to phrase that differently, but the basic recurrence that's going on here is we have this integral in d dimensions, and we're going to take one of these dimensions and I guess move from integrating over that dimension. We're going to approximate it by applying a quadrature rule along that dimension, and then we're going to pretend that we can integrate exactly along the other dimensions. So I guess this should be approximately equals. So we're going to do the same sort of thing where we have the nodes in 0 to 1 and the weights of the quadrature. And we're going to sort of just assume that we can evaluate this integral here. And we're going to sum up a bunch of different versions of this integral with different fixed values in this spot here. And if we do that, we should, I guess we're able to reduce this d-dimensional integral here to a d-1 dimensional integral here. And I guess we can do the same thing again, where we just turn this integral into, well, here we turn this d-dimensional integral into a sum over one dimension and an integral over the remaining d-1 dimensions. This integral that we have left here, we can turn that into another sum and then an integral over d-2 of the dimensions. And then we're going to take this element of the vector and fix that in each version of this integral we're computing. And we're going to sum over all of the possible nodes that we could put here. And then whatever quadrature rule we pick for one dimension, we're going to use that weight again here. And so in the end, I guess we get, we're going to get a nested summation with a bunch of omegas out the front of the term, and then eventually we get down to, I guess it'd be a zero-dimensional integral here, which is just the function. So we get rid of all these integrals, and we just have a product of a bunch of omegas here, a bunch of nested summations here, and then just the function value, and we're going to eventually be able to fix all of these points. And when I say fix, I guess I mean each of these variables is going to get replaced by a summation variable, which just takes on the values of the nodes at which we're computing our one-dimensional quadrature rule. So we have a bunch of sums, a bunch of weights multiplied together, and then the function value at some d-dimensional node whose elements are nodes of the one-dimensional quadrature. And I guess if we want to write that very compactly, we could say that we're summing over all combinations of this WG, where this is just a product of omegas. The particular omegas we pick, well, here we're summing from 1 to n, and then from 1 to n, so this can be anything from 1 to n. This can independently be anything from 1 to n. So I guess for each of the dimensions that we have a sum for each term in the sum, we're going to need to take each of those dimensions and give it a value from 1 to n. And that is the first weight in the quadrature needs to get picked. The second weight in the quadrature up to the nth weight in the quadrature needs to get picked independently for each one of these. So I guess we're going to have n to the power of d different terms in this summation. So n to the power of d different combinations of these omega indices. And then n to the power of d different combinations of the the nodes that fill in each element of this vector that is the argument to this function that we sampled the multidimensional function at. So yeah, I guess summing it all up again. Yes, so to summarize, we're just applying the one-dimensional quadrature rule to the innermost innermost integration, and we sort of continue that process, commuting this sum with this integral, so swapping those two around, and we end up with a way to turn a one-dimensional quadrature rule into a multi-dimensional quadrature rule, which I guess is sort of convenient. The only trouble with this is that this n to the d grows very, very quickly as we increase the number of dimensions. So I guess that's what this curse of dimensionality is talking about, is the fact that when you apply this tensor product rule for turning a one-dimensional quadrature rule into a higher dimensional quadrature rule, the number of points at which you have to sample with a fixed number of one-dimensional nodes n grows exponentially. So if n is 2, it'll grow like 2 to the d, so 2, 4, 8. If n is 3, it'll grow even faster. And usually in one dimension, to get a decent quadrature, you need quite a significant number of nodes, even in one dimension. And so if you're going to take that rule and extend it to a higher number of dimensions, it's going to be very, very slow to get a good estimate of the integral. So I guess that's what this question from 2012 is asking us to talk about. The second part of the question asks about the Monte Carlo method. And I guess if you remember from the lectures, the Monte Carlo method is, rather than going through all of these n to the d different nodes at which to sample the function, rather than doing that, we can select the places at which to sample the function from a distribution. So like it could be a normal distribution or some other random distribution. I guess in this case you'd want it to be the uniform distribution on the hypercube. And basically the reason for that is the integral of this function over the d-dimensional unit cube. Well, that should be the same as the expectation of the function if you sample uniformly from this domain of integration. So if you sample these x's randomly, and you take the average of a bunch of those, well, the average, if you take enough samples, should be fairly close to the expectation. But that is the same as the integral of the function over this domain that we care about. And so if we look at the root mean square error of the Monte Carlo method, it's a constant that I guess depends only on the structure of the function. And then it's proportional to n to the minus a half. So there's this 1 on square root of n. And this expression here for the root mean square error has no dependence on d. And so we can sort of say that because it only depends on this sort of feature of the function, which is called the variation of the function, and this term in terms of the number of samples that we take, it doesn't actually directly depend on the number of dimensions that this function has. And it turns out that this variation isn't strongly affected by the dimension of the function. And so because of this, I guess we can say that the Monte Carlo method doesn't have the same problem that this tensor product rule has, where we need a very large number of samples to get the same level of accuracy. Cool, so I guess here's a practical question in terms of that formula that we saw before. Yes, so we're going to use a Monte Carlo simulation to estimate the value of an exotic option. So this is going to be some integral, some expectation that we want to estimate by choosing random samples, evaluating the function there, and then taking the average. And we're saying that if we use 10 to the 6 samples, we get an error of 1 cent. And we want to know the number of samples we would need to take if we want an error that's 1/10 of that. So 1/10 of a cent error. And I guess the sort of reasoning we can do here is, well, we don't know what this variation of the relevant function is. In fact, we don't even know what the function is. It's not specified in the question. But we know that that will be fixed with respect to, it won't vary with respect to the number of samples that we take. So if we see that the root mean square error is some constant times 1 over the square root of the number of samples, and here the number of samples is 10 to the 6, producing an error of 1 cent. I guess we can sort of equate these. We can say that 1 cent is going to be whatever constant that was, the sigma f for the relevant function, which we don't know, times n to the power of negative half. And if we assume that this holds, well, then we can crunch the algebra here, and we can actually work out the value that alpha should approximately be. And so now we have the constant of proportionality, and we can actually set up another equation, which is just the error that we desire is, well, we know it's proportional to n to the minus a half, where n is this new number of samples that we're trying to find. But because we know the constant of proportionality, we can actually plug it in now. And we can deduce that the new value of n to get an order that's 1/10 of what it was before is 10 to the 8. And I guess that sort of makes sense because it's 10 to the 6. And then you need 2 more factors of 10 because of this negative 1/2 exponent. So yes, we get this final answer of 10 to the 8. Cool. All right, so I guess the next bit is talking about random numbers and simulation. I guess the idea here is that, well, in order to do Monte Carlo, for instance, we need to produce random numbers from whatever distribution that we want. And you know, we don't immediately have access to random numbers, but computationally there are ways to generate numbers that are, for all intents and purposes, essentially random. And these are pseudo-random numbers. So, for instance, I can ask MATLAB for 10 random numbers uniformly distributed between 1 and 10. And, you know, it's not just pulling these out of thin air. It has some sort of algorithm in there that is deterministic, but mixes the numbers up sufficiently and generates a sequence of random numbers that has the distribution that I want approximately, and looks random to the point where I can treat it as essentially random, even though it's coming from this deterministic process. So this gives us a way to produce uniform random numbers, but potentially we want random numbers from arbitrary distributions. So in order to do that, we can one way to produce numbers from an arbitrary distribution in one dimension at least is using this inverse transform sampling method. So the basic idea here comes from the fact that if you take the cumulative distribution function of a random variable and you apply the function to the random variable, you get back a uniform distribution. And if you think about the implication of this property, because the cumulative distribution function has an inverse function, if you're saying that CDF of the random variable is uniform, that means that the random variable is the inverse CDF of a uniform random variable. And so one way to get a random variable with whatever distribution you want is to take a uniform random variable and apply the inverse cumulative distribution function. And that's what we're concretely doing here. So x is going to be a random variable with this probability density function, x squared over 9. And this first part of the question is asking us to find the inverse cumulative distribution function corresponding to this PDF here. So step 1 is just find the cumulative distribution function. And then I guess after that we can find the inverse function to that. So to find the CDF, we want the probability that a random variable with this distribution is less than a given number. And because the support of the random variable is 0 to 3, we can integrate from 0 up to whatever number we want. We can just integrate the probability density, and this will give us the CDF. So if we plug this in here, we can, well, this is t squared over 9 is the PDF, and we integrate that, we get x cubed over 27. So this gives us the cumulative distribution function of the random variable. Cool. And then if we rearrange this equality here with the first and the last expressions, well, this is x cubed over 27. So we can bring this 27 over here. We have 27 times the CDF is x cubed. And that means that if we take the cube root on both sides, 3 times the cube root of the CDF is equal to x. And then if we replace x here with the inverse cumulative distribution function, well, then inverse p of x is just x. And then over here we get inverse p of x. And so this lets us deduce that the inverse cumulative distribution function is just 3 times q beta x. Cool, so that's pretty much just algebra and integration. So yes, now what this lets us do, now that we have this inverse CDF here for this random variable, suppose that we have a uniform random variable. Well, we said before that if we apply the inverse CDF to the uniform random variable, then we can generate samples according to the distribution that the inverse CDF corresponds to. So in that case, that's the random variable that we've set up here. So this is running through the same reasoning I discussed before. P of x follows a uniform distribution. We're just applying the CDF of a random variable to itself. And y is this uniform sample that we have. So that means that P inverse of y is just going to be is going to have the same distribution as x, and P inverse of y is concretely what we calculated here. So 3 times the cube root of the argument to the function. So if we want to generate samples from this arbitrary distribution x, what we can do is we can generate these uniform random samples, which we've seen how to do. And then we can apply this inverse cumulative distribution function to get samples from this original distribution that we wanted. So in MATLAB, I guess the way to do that is we can generate these 10 uniform samples here and apply the inverse CDF, and then this x should follow the distribution that we wanted, which is this x squared over 9 distribution. So I guess we might as well try this out. So we have these uniform random samples here, and then x should be, I think we said 3 times these uniform random samples raised to the power of a third, so cube root of those. And now these x's, we can see that these are all between 0 and 1. These x's now range from 0 to 3, as we wanted. And they should follow this original PDF. Will describe, I guess if you plot a histogram of these x's, this original PDF will describe what that should look like. Cool. All right. So now we're going to think about a little bit more about Monte Carlo methods, and in particular using Monte Carlo methods to compute the expectation of a function with respect to some probability distribution. Yeah, so this question from 2016 is basically just asking us to explain how the Monte Carlo method helps us compute this expectation. And yeah, I guess so if we want to compute the expectation of this function with respect to some probability distribution, the expectation, you can think of that as the long run average of the output of the function. As we sample from this distribution, plug it into the function, and look at what number we get. So if we're interpreting this expectation as a long run average, well, one way to estimate the long run average is just to take sort of a medium run average with a finite number of samples n. And we can sample the arguments to the function from whatever distribution we're integrating with respect to. Sample from this distribution, plug it into the function, and that takes our samples from this distribution. We now get a bunch of samples from the output set of the function. And so these samples here, if we average those, that should give us an approximation to the expectation of the function with respect to the probability distribution. Cool. So hopefully that all makes sense. That all checks out intuitively. I guess a concrete example would be, if we wanted to estimate the expected value of the square of a normal random variable, what we could do is we could set that up as this integral where we have f is x squared, and then p of x is just the probability density function of a normal random variable. And so that's how to represent it in integral form. If we want to approximate it empirically, then we could sample a bunch of normal random variables, these xi, square them all and take the average. And that should give us an approximation to the expectation of the square of a normal random variable. Cool. So I guess one sort of drawback of this Monte Carlo method is it is a random method or a pseudo-random method. Because of this, there's going to be some noise in the estimate beyond just the error that we would expect to get from sampling only a finite number of inputs to the function. So I guess if we think about the overall error of our estimator, well, I guess the thing that we want is, as n gets very large, we want this error to get smaller and smaller. If we think about it concretely, we can think about the squared difference between our estimate and the actual expectation, which is just a fixed number. I guess one thing that is worth saying beforehand is that the expectation of our estimator is actually equal to the value that we're estimating. When I say the expectation of the estimator, what I mean is if we're taking a Monte Carlo estimator with 10 samples, if we take a new 10 samples and compute the estimator, and then a new 10 samples and compute the estimator, and so on, in the long run, the average of all these estimator values is actually going to be equal to the number we want, which is kind of a nice property to have this be unbiased, meaning that the expectation of the estimator is equal to the thing we're trying to estimate. And so because of that, when we compute this squared error of the estimate, so this is the estimate minus the true value squared, and then we take an expectation, well, this is actually equal to the variance of the estimator. And the reason it's equal to the variance is basically because this expectation of f is actually the expectation of this. So we can interpret that as just the variance of this expression of the estimator. So if we write the estimator out explicitly, we have this variance of this, I guess this constant term, this term in terms of n times this summation. And because of because of I guess theorems from basic statistics, the way this estimator, the way this variance operator behaves is we can take this n factor out as an n squared. And then because these xi all come from the same distribution, all of these f's will also come from the same distribution. And so the variance of the sum will actually, there should be an n here. This variance of the sum will be n times the variance of the individual sum n's divided by n squared. So this works out to 1 over n times the variance. And then this should be the square root of the variance of the individual samples divided by the square root of n. Cool. And that is the, you can interpret that as the root mean square error. You can also interpret that as the standard deviation of this estimator as a function of the number of samples. And because we have this, what should be a square root n on the bottom, we can see that as n grows very large, the standard deviation of the estimator gets smaller and smaller, which means that this estimator is going to get closer and closer in the typical case to the actual value that we want to estimate. Cool. So now I guess we can think about different tricks we can do to reduce this root mean square error even further, beyond just increasing the number of samples. So one thing we can try to do, basically the reason we're using Monte Carlo here is we don't have an analytic expression for the expectation of this function f. If we want to reduce the variance of our estimate, one thing that actually helps is if we can find a function that is reasonably close to this f, for which we do have an analytic expression for the expectation of that function with respect to the distribution. Yeah, so I guess maybe just to think of an example off the top of my head, perhaps you could estimate cosine of x as the cosine of a normal random variable, for instance. You could estimate that using using a quadratic Taylor approximation to the cosine function. You can compute analytically what a quadratic function of a normal random variable, what the expectation of that should be. You can compute that analytically using the moments, because that will just be some constant term plus some linear term times a normal random variable plus some constant times the square of normal random variable. And it turns out that all of those have analytic expectations. We can write down a formula for what those should be. So that's maybe one concrete example where g would be the quadratic approximation and f would be the actual function, the cosine function. So yeah, I guess the concrete steps that you take in this case, if you want to use this approximation, is you look at the difference between f and g. And this is sort of the component of the expression that is difficult to integrate. And so that is the part that you estimate with Monte Carlo, this f minus g. But then everything that's left over, you just put in this expectation of g, which we have an analytic expression for. And so your estimator for f is just going to be the explicit formula that you have for the expectation of g, plus the Monte Carlo estimate of the difference between the functions. And as n gets very, very large, this term over here should just tend to the expectation of f minus g. So if you have the expectation of g plus the expectation of f minus g, that should just be the expectation of f. And by writing it in terms of a Monte Carlo estimate of f minus g rather than a Monte Carlo estimate of f, because these f minus g will tend to be smaller than f, assuming that the approximation of g to f is a good one, because these will be so small, the variance of this Monte Carlo estimate, which is actually the variance of the entire estimator, is hopefully going to be smaller than if you just took a Monte Carlo estimate of f. And because this variance is smaller, well, the square root of the variance divided by the square root of n will also be smaller. So the root mean square error of the estimator will be reduced, even with the same, taking the same number of samples. So this is a way to use approximately the same amount of computing power to get a significantly better estimator of the true expectation of this function. Cool. Yes, so this next bit is also a way to reduce the variance of a Monte Carlo estimate. And it basically comes from this idea of decomposing the function into odd and even components. So this is sort of just an algebraic trick. If we take a function f, and this could be any sort of function, if we just take a superficial look at this right-hand side, well, we have these 2's in the denominator, so we can combine the numerators of the expressions. If we combine it, well, we'll get 2 copies of f of x, and then these f of minus x's will cancel out. So in the numerator, we'll just have 2 copies of f of x, in the denominator we'll have a 2, and so clearly this identity is correct. Why is this identity significant? Well, what we've done here is we've written f of x in terms of the average of f of x and f of minus x plus the average of f of x and minus f of minus x. And it turns out if you think about this term over here, this term over here is going to be an even function in the sense that if you plug in minus x, you get the same value, because you'll get a minus x here and just an x here, and then you've basically just swapped these 2 terms. So this here is an even function, and it turns out that this component here is an odd function in the sense that if you plug in minus x here, you get the negative of this term. And so even though this original function f of x was neither an even function nor an odd function necessarily, we sort of decomposed it into the sum of an even function and an odd function. So if we think about, suppose that these x's, I guess, are sampled from a function that happens to be symmetric about the origin. So an example of this would be x is a multivariate normal random variable with a mean vector of 0. Or I guess a simpler case is just x is a single-dimensional normal random variable with an average of 0. So if we think about sampling x from a symmetric distribution, symmetric around the origin, then we can think about the expectation of f with respect to this distribution as being the sum of the expectation of the even term and the expectation of the odd term. And then I guess the reason for doing all this setup is this expectation of the odd term here for a symmetric distribution. It turns out that because plugging in minus x to this term gives you the negative of the term. Because the distribution x is symmetric, the expectation of the odd part of the function is always going to be 0, exactly. And so because of this, I guess we can we can think about this as approximating f by its odd part, and then applying the same sort of technique that we had before is one way to look at it. A different way to look at it, I guess, is that whenever we sample a particular x and add that to our list of samples that we're going to average over, we can imagine also adding an identical negative x sample. And the reason this is valid to do is that the distribution we're sampling from is symmetric. So sampling x is as likely as sampling minus x. And if we always add the negative of every sample into the pile of samples we're going to average over, we're going to eliminate this odd part of the function. And so the sum end here, we can actually just write that as the even part of the function. So I guess that's two different ways to look at this method of antithetic variables. And I guess the thing that we hope for here is that by doing this, by getting rid of this extra component of the function, we will reduce the variance of this estimator of the function, this Monte Carlo estimate. I guess one thing that's not so great about this method is it very much requires that the distribution we're sampling from is symmetric. Because if it's not symmetric, the expectation of this odd term will not necessarily be 0. And so because of that, we really can't apply this method anywhere else except where this x is symmetric. If it's not symmetric about the origin, but it is symmetric about a different point, potentially we can do a translation change of variables to fix that problem, to turn it into a problem where x is symmetric about the origin. But otherwise this method is not really as general as this previous method here. Cool. So I think this is the last thing we're going to talk about in this topic. And that's quasi-Monte Carlo methods. So Monte Carlo methods, we were taking pseudo-random numbers and using that to estimate the expectation of a function with respect to a distribution. Here we're sort of going more back to the problem of quadrature, rather than the problem of specifically estimating an expectation. And rather than using pseudo-random numbers, we're now going to use a sequence which, if we look at this picture here, pseudo-random numbers will tend to sort of clump up, and I guess sample function values that are fairly close to one another in the domain of the function. And if the function is sort of smooth and continuous, that will tend to mean that these are samples that are close to each other in the x's will also be close to each other in terms of the output of the function at that point. And so we're sort of getting a lot of samples that are very highly correlated with one another, which is maybe not so good. So we can actually construct a deterministic sequence of points, which is a little more evenly spaced out. And I guess this inequality, which I'm not going to try to pronounce, this is sort of giving us a guarantee about the absolute error of an estimator of the integral using this sort of quasi-random sequence rather than a pseudo-random sequence of numbers, in terms of what's called the discrepancy of the quasi-random sequence and the variation of the function, which is a term that we saw before. This was the sigma f that came up in the Monte Carlo estimate. So this question from 2017 is basically just asking us to explain what a low discrepancy sequence is. So I won't go over again the definition of the discrepancy here. Basically, the solution that sample answers give is just a sequence is called low discrepancy if this discrepancy here of every prefix of the sequence, so that's the first term, the first two terms, the first three terms, and so on. If we look at the discrepancies of all the prefixes of the sequence up to some n, we want that to be bounded by a constant multiple of this expression here, log n to the d divided by n. And this is basically just the definition of what it means to be low discrepancy. But if we do achieve this low discrepancy, that gives us quite a tight bound because of this inequality well, I guess it gives a tight bound to the absolute error of this function divided by the variation of the function, which hopefully is reasonably small. And so I guess if we sort of ignore this variation, this is giving us a fairly tight bound on the absolute error of this quasi-random estimate to the quadrature problem that we have here. So I guess that's the reason we care about the sequence being low discrepancy. And when we talk about low discrepancy, this is the particular expression that we're looking to bound the discrepancy of the prefixes by. Cool. And so I guess this second part of the same question from 2017 is asking why this might be preferable to a Monte Carlo method. And I guess numerically you can compare the this bound here, discrepancy times function variation. If we treat function variation as a constant with respect to the sample size, basically we've shown that the absolute error of the quasi-random quadrature estimate for a low discrepancy sequence is proportional to this expression, log n to the d divided by n. And that was just this here, by the definition of a low discrepancy sequence. If we compare that to the root mean square error of a Monte Carlo quadrature estimate, this root mean square error is going to be proportional to 1 over the square root of n. And if we sort of just compare these, we want these to both shrink as fast as possible as n gets larger and larger. And if we look at this here, well, this exponent of -1/2 is larger than this exponent of -1, which means that this is going to shrink slower than this first part here. Once we multiply by log n to the d, there is some dependence on the dimension, but log n to the d is always going to be still less significant than n to the power half, which is what we need to have here instead to get this. So if this was n to the -1 times n to the 1/2, this would be just as slow as this is to converge. But because we have this sort of smaller term, log n to the d, I guess the upshot is that this quasi-random, this quasi Monte Carlo estimate of the quadrature problem has a faster convergence guarantee in terms of absolute error than the Monte Carlo method has in terms of root mean square error. So not only is this deterministic, but if we sort of try to compare, the error of 1 in terms of the deterministic error and the root mean square error, which is statistical for the Monte Carlo method, even in terms of that, this quasi Monte Carlo method for a low discrepancy sequence is still better. Yes, so that's basically all of 8 and 9. Yolanda will be on in a couple of minutes to present 10 and 11. If you have any questions, feel free to pop them into the chat. If you have questions after the session, you can ask them on Discord or Facebook. Either of those is fine. Cool.
Hello, can you hear me? Hello. I think this should be fine. My internet might not be that great, so let's see how we go. Yeah, so let's just begin, and if there are any lagging and stuff, I am on the stream as well, so just pop a message into the chat and I should be able to see. Alright, okay, so let's get going. So, hi, I'm Yolanda, and I will be holding the revision seminar for chapter 10 and also chapter 11. So let's just get going. So firstly with chapter 10, it's about stochastic integration in SDEs. And the first topic inside this chapter is something about random walks. So I'm not going to go into too much detail about the contents. I will focus on some of the example questions later on. But in short, random walks are basically a sort of model where the current step doesn't necessarily depend on the previous steps, or it has a very little dependency on previous steps. And essentially, to actually have the modeling, we firstly need an increment. So let me just change color. So firstly, we need an increment. And sorry, there's a typo over here. So essentially, the delta xn is going to be at the current step, we need to predict the next step, and this delta xn is what we add on to the current steps in order to actually have the random walk moving on to the next step, which is our xn plus 1 over here. And just by formula, it has the form of xn equals to mu delta t plus all of these stuff over here. And note that inside this formula, this mu over here, sigma, as well as the gamma over here, they're actually all constants that you will be able to find out or will be given to you inside a question if a random walk question does pop up during the exam. And some of the derivations, or rather some of the results that we have from the random walk is these two over here. And I will go into detail about these two formula and a little bit of derivation with it for the next question, example question that we're going to go through in a bit. And Moving on from here, if we know the first starting point of the random walk being a constant with certainty, then essentially we can also derive these two things from this two formula above. So firstly, we know the expectation of xn, which is at the current step of this random walk process, is going to be this constant over here, which is our initial value, with this constant mu and our time t. And when our gap, which is the period of each of the random walk approaches 0, meaning that the scatter goes from, let's say, if delta t is this big, which is kind of like, that something, I don't know, just an example like that, where delta t is a constant and it's fixed, to something that's a lot more crushed together. I don't know a better way to describe it, but essentially as the delta t moves to 0, we will have more frequent walks, or our walkers, presented on a graph inside our predictions for stocks or any other things like climate change or other examples. And for the variance, we actually can separate it into 3 cases. That's totally depending on our gamma over here. And if you realize, the gamma is actually one thing that's presented over here. And from this bit, it's pretty trivial to see that a half is actually a very important value over here, where it's actually, when it's actually equal to or less than a half, depending on the formula over here, they will actually give you different values where the variance will approach. And from these 3 cases over here, we can see that we obviously want to choose something that is numerical, and we can actually use to gain information for the random walk or the variance of the model. So we usually choose this constant over here when gamma is actually equal to a half, and our variance can be predicted using the values of sigma and also our time period t. So moving on, this is just basically reiterating what I just said. We choose the constant value of gamma equals to a half to actually get a non-zero finite variance. And from this choice of gamma, we can rewrite the above equations, which is over here. We can rewrite this equation over here, just circle it, in terms of a half. So essentially it's the same thing, where you see that the gamma becomes the square root, and in order to predict the next step, xm plus 1, we will just have xm plus this value over here, which we have put in the model, which is basically the same thing as above, but just substituting a value in. And with the stock price Sn, the model's relative change can also be calculated using this random walk formula over here. So you see that this is really just the same thing as that. And over here, we can calculate the relative change, and it kind of makes sense that our current step is of the stock price is Sn, and the change in stock price is given over here. And this change in stock price, or the relative change in the stock price, is really just what we have predicted over here, which is the delta xn at the current step. So it kind of all falls together, what it's about. So now moving into a past paper question. Before that, let me just check the chat. Everything's fine? Okay. So let's actually move into one of the past questions from 2022, question 3 III. And it's a pretty simple and straightforward question that talks about the random walk formula, which you can see it's exactly the one that we have just talked about. And during the final exam, I do know that you can bring in a cheat sheet. Usually they won't, at least when I did the course, all of the formulas will be kind of given by the question. They don't expect you to actually remember all of these formulas by heart. So yeah, depending on if you have enough space inside your cheat sheet, you don't really have to drop the formula down because they will be provided most of the case. But anyways, going back onto the question, we know that these z's over here, so from 1 all the way to n, They are independent standard normal variables with an expectation of 0 for all of them and a variance of 1 for all of them. So that's just the basic definition of this. And we also have a definition for another constant over here, which is t over n, and we know from the previous definition that this is basically the time period, the little delta t that we have described in the previous page over here. So now moving on, we want to firstly write a MATLAB code which generates the random vector of the x, and we see that the x1, x2, x3 really just is a follow-on from this equation over here. So if we want to calculate, let's say, for instance, x2, then we would require the previous step, which is our x1, to actually do that. And to give you all of these, we have to start with something that we know. And the thing that we know is the z's, the standard normal variables. So firstly, we can just use the MATLAB function rand_n to give you a vector of random standard normal variables, or our RV. And this is really just copying whatever is over here, so whatever is inside the equation. And we see that this is getting messy. Let's get rid of this. And we see that this bit that I've highlighted over here is this bit over here. So it's just really putting the definition in. And in order to change the vector into something of this form, which is every single random variable added together, we use another MATLAB function, which is called cumulative sum function. So over here, this one over here, and it basically just calculates the cumulative sum of a vector. So let's say if we have a vector of e1, e2, e3, it just basically calculates e1 plus e2 plus e3, etc. And finally, we add x0, which is our initial value over here, onto the function, sorry, not to the function, onto the value, and we obtain what we want from the question. So pretty simple thing to do. And part B is what is the distribution of xn. This should be also pretty trivial because from the equation we know that, well, alpha and our beta and all of these are all constants, and these two, the xn minus 1 and the xn, they are really the same thing, just that it's a recursive process, so it's part of the equation. So the only thing that affects the distribution will be the distribution of the Zn, which is already given. So that's a standard normal variable. So after these additions, multiplications and stuff, it just really is a normal distribution. So that should be pretty trivial to follow. And finally, part C is find the mean and variance of xn. So again, we start with the formula. And inside this one, obviously during exam, you don't have to write so much and so comprehensively about all of these. I personally wrote a bit more just to explain the derivation of this bit over here a little bit as well. So I will explain bits of the derivation using this question and hopefully make sense to you which part should be required inside exams. I'll highlight the parts that kind of you have to write inside exam in a bit as well. So again, before we attempt to actually find an expectation of xn, we have to rewrite xn in the given constants, and the constants are the ones that I've circled above, the alpha, the beta, and etc. So firstly, we have the formula. I just rewrote it down so I have a reference over here, and essentially what I'm doing is I'm moving this term to the left-hand side to actually get everything that is part of our random walk procedure to the left and the constants to the right. And you can see this is essentially just repeating all of our formulas for n and an n minus 1 all the way to the first random walk that we have, which is x1 minus x0, where x0 is given to be a constant as well. Then what we do is with all of these equations above, we sum up all of these equations, and there are n of them because, well, n is from, in a question, n is from 1 all the way to capital N. So there are capital N of these equations, we add them all up, and by cancellation we can see that this term will be, this term will be cancelled out by that, this will be cancelled out with this term, which is not written, and x1 will be cancelled out with something above. So essentially on the left-hand side, we only have xn minus x0 left. This should be pretty easy. And on the right, these are all constants. These are all the same. There are capital N of them. And over here, these are all the same. So we put it out, and we have all of these examples over here. And now remember that we have x0 as a constant, and we know the value of here, which is already given inside the question. Again, I'm just dropping it down. So to actually do the calculation, we move this constant again back to the left, right, and then we have this, and that is just immediate follow-on from this equation over here. So we simplify it down. This is the same, and this is the same. And now with this equation over here, we can see that xn is somehow already expressed inside all of the constants given by the question that we know. And from this step onwards, we can actually calculate the expectation. So again, by the linearity of expected value, we can separate the terms apart. And because this is a constant of the expectation of constant value is just itself, this one as well. And over here, this is a constant, so we can bring it out. And we know that for each of these terms, they're independent. And so we can, again, linearly separate it out. And because there are standard normal variables, the expectation is 0. So everything just becomes 0 for this final term. And we obtain the solution. So the solution is just over here, this one over here. So reiterating back to what you actually have to write inside exams, obviously you don't have that much time. All of these are kind of just not needed. This is just a derivation that I personally want to go through just to make more sense of it. And essentially all you need is this over here. Yeah, so you need this line over here for sure. And something depending on your choice, this and that. So this is what, and this line, I will personally put it in as well. So these are the step you want, and personally, I would write linearity of expectation just to be safe. But again, like this is very basic stuff, so I don't think they care that much about what you write. Oh, there's a typo over here, sorry about that. And similarly, for the variance, it's really talking about the same thing. So this is a variance, this should be a variance over here, sorry about that. Again, because all of these variables over here, or really their constants, are independent to each other, so you can separate them out again one by one. And then variance of constant is 0, so the first two terms gets cancelled out, they're all zeros. And when you take out a constant outside of the variance, we have to square it. That's where the square come from. And again, these are all independent standard normal variables, so we can separate out one by one. And I'm missing a bracket over here. We know standard normal variable, each of them will have a value of 1, so there are n of them, that's why this n came. And then again, these two combines to give you t, that's given a given formula inside a question. So nothing too hard about that question. It's really just some algebra, and it should be trivial to do by now. So the next topic inside this chapter is our Wiener process. Essentially, all you have to know about Wiener process that is kind of will be given inside exam are the key properties. So I will highly recommend dropping these 4 key properties of Wiener process down inside your cheat sheet, because you will see in a bit as well, it has been tested for you just to copy these 4 things down, and that's easy mark to get. So here are the key properties. It depends continuously on the range that's given. And secondly, oh, this shouldn't be an O, sorry about that, but W0 should be equal to 0 with a probability of 1. So it's certainly know that it starts with a value of 0. And the next thing is really just talking about the how Wiener process relates to our normal distribution with a expectation of 0 and with a variance of t minus s. And given that s and t are just 2 time instances within the given range, big T. And finally, this one is just talking about the independency of Wiener process, given that the time period doesn't overlap. So that's the most important thing over here, I would say. We need to make sure that the subtractions of the time period when given inside a process, they don't overlap. It's two separate periods within the entire frame of time. And essentially, Wiener process will lead on to two integrals, and it looks pretty complicated, and to be honest, I don't even know how to fully derive it myself. But essentially, what you have to know about these integrals are these are the integrals, the Ito's integral, and I'm not going to attempt pronouncing this. The two consequences or the two required integrals to actually go on to Black-Scholes model. So we use this to derive what is very important in the topic of financial maths. And these are the formulas over here. You can do some research on at your meantime. I'm going to skip over this because it's not that important inside a final exam. And finally, we have the stochastic differential equation, and we just have to know the xt, which is a function, would satisfy the differential equation. And Ito's lemma is again a thing that we use to derive firstly the Ito's integral, and secondly the Ito's integral will be used to derive the model that we talk about a lot. So these are the equations. I've put it down. But yeah, I haven't seen in my memory that these has been tested. Maybe in earlier years, yes. But if you do have any questions with these, feel free to drop a text or something inside our Facebook chat, or just DM inside the Facebook pages, and we will try to help you understand these formula better. And essentially with the two integrals above, these are the properties and the things that I want to drag your attention to. Firstly, we know that for this one over here, it looks into the future to the right-hand side of the endpoint. So it kind of is more complicated in a sense because it has the ability, I'm missing a bracket. It has the ability to kind of look into the future instead of just focusing on the current, where if you compare it to Ito's integral, it kind of doesn't have this property over here. So you see that the difference is really with here. And secondly, it's just the ordinary chain rule that we all know how to do from high school, and it's often used in physics. And for Ito's, it focuses on the current value, which is the current instance of the integral, and then the chain rule follows Ito's lemma, which is the one that's stated above. And finally, it's used in finance to do calculus and stuff. So that's basically an overview, a very brief overview with all of this stuff above. And let's actually move into a question, which is the most important, more important thing over here. So we know that we have an asset price ST, and it follows the Brownian motion. Brownian motion will be briefly introduced later on as well, so I'll go on more details about this later. And we know that WT is really a Wiener process, and they have constants. So the first question, as I said, they ask you what are key properties of Wiener process, and all you have to do is to drop these 4 things down. I don't know if it's going to be tested because it's open book, so obviously you can just drop this into your cheat sheet, but who knows, they might just give you an easy mark over there. So moving on to the second question, part B, we have equation 1, which is the one given above over here, and it can be written using this form over here, and hopefully this looks familiar to you. We talked about this at this 3rd page of today's presentation over here. Where is it? Yeah, over here. So it's the model relative change that we have kind of mentioned above. So now going back to the question, again, by the definition, we know that the Z are just independent standard normal variables, and these are the definitions that's given. More importantly, we can see that the asset price, the change in asset price is really just whatever asset price that you will have in the next instance minus the current instant, and that makes sense. So now we have we can generate an independent example of U's, and they are uniformly distributed. So how can these example used to simulate asset price? So it seems to be a pretty complicated question if you look at it by itself, but luckily this is actually a follow-on question from question 3I in the same year. So question 3I basically asked you to show that the CDF of a real valued random variable is uniformly distributed in the interval over the interval of 0 to 1. So essentially what it's saying is that if you have uniformly distributed wrong way around. If we can apply the CDF function to the uniformly distributed random variables to obtain normal samples. That's essentially what this question from the same year told you to do. So with this result that we have already proven from above, and even if you didn't prove this result, you couldn't quite get to it, you can still use it. So that's a good thing about it. So we know that with this derivation, we can apply the inverse of the CDF to the uniform samples to actually obtain normal samples. So essentially what we've got, but in reverse order. And of course, we have to assume that firstly, inverse is available. And to actually assume that inverse is available, we have to assume that the function is kind of increasing because that's a property of CDF. And with the inverse, we can let the inverse of the CDF be phi inverse. Then we can have we can obtain the Zn, which is what we want inside a formula, the standard normal random variables, by inversing these independent samples that we can generate out. So with this, we can obtain the Zn, and the process basically just immediately follows on from this example over here. You see that this bit here is the same over here, and this change really just follows from a immediate rearrangement from by substituting the delta from this equation over here. So essentially you just put this into that, rearrange it, you'll get this equation over here, and that's all you need. So this is part B, and this is the end of this question. Now the next bit, which is a pretty big topic in financial mathematics, or in a sense options and pricings, is Black-Scholes principle. And to start off with this, we have to kind of introduce what is geometric Brownian motion. And you see that the Black-Scholes principle starts by proposing the asset price dynamics by obeying this geometric Brownian motion, which is this equation over here. And again, if they are going to test you or tell you to derive something using Brownian motion, they will provide this formula for you. But you should recognize that this is talking about the Brownian motion. And we know, again, the mu and sigma over here are constants, and we have to also have an assumption where at the time or the instance where we just begin the asset price, this asset price should be greater than 0. And there are a bunch of derivations for this inside the lecture slides, which I'm not going to go into, but one thing that I want to draw your attention to is that ST, this thing actually follows a log normal distribution, and you can actually do change of variables and a lot of some transformation to obtain the log normal distribution. And inside the lectures, they talked about the change of variables and stuff as well, which I didn't really include inside my slides, but I will touch on it inside a question later on. So that's all I want to talk about over here. And the Black-Scholes PDE is this thing over here. It looks complicated again, and it seems to not make too much sense with all these notations of, okay, what is T, what is V, what is SS. But again, inside exam questions, they will make it pretty clear to you what is what. They will define everything carefully for you. So that's the PDE, and From the PDE, again, you do some integration, differentiation, and stuff to obtain the final summary or the results that is the most important to us right now, which is the summary over here. So firstly, we define the VST to be the value of the option, and S is the asset price at the current value, or we can say it's the market value at the current timing, and T is just the current time. And it follows this differential equation, or the PDE over here. And we see that the asset price is from 0, makes sense, and to infinity, given that they have the ability to go infinitely large, and we have a set period of time between 0 and t. So in the case where V is a call option, we have these results over here, and obviously the value of the European options can also be a put option. And I believe that Odin has went into some explanations of what is the call and put option in chapter 7, and I will also do a quick review of this later. So for the sake of now, let's focus on the first one, which is the call option. So just to have your memory back, call option gives you the right but not the obligation to buy a option, and put is just vice versa. It gives you the right but not the obligation to sell. So when the call option is equal to 0, meaning that you're buying the option for sorry, wrong way around. Okay, when S is equal to 0, so when the market price is equal to 0, then you don't want to exercise the call option, right? Because let's say you set the call option at $10, but right now the market price is 0. Then why don't you buy for 0? So in this case, the call option is worthless, and that's why we have C equals to 0 over here. But when S approaches infinity, meaning that it's really, really expensive now, it's worth like $1,000 or something, then in this case, and be very careful, the condition is that we haven't reached the exercise or the expiration date yet. T is the expiration date. So at that case, you would most likely want to exercise your right to buy at the expiration time. So in this case, it's just whatever value of the exercise price that you have. So S is the current market price, and you minus off the current value of the stock, and then that gives you the call option at the current period of time, or current instance. And finally, at expiration, where S is between the bounds that we have defined, inside this case, we take the maximum. So this plus means maximum. So it's essentially the same thing as, very bad writing, but essentially the same thing as saying that. So I'll explain this in a bit as well. It's at the slide over here, so I will get into that in a bit. And similarly, the same thing, but in reverse, we have our put option. So you probably can look at this by yourself. It's really the same thing. You see x minus k turns into k minus s for the same condition and stuff. So that's about the put option. So now actually getting into the time at expiration. We have two cases. One is 0 and one is S minus K. Just to reiterate, S is the current market price, or we say the asset price, and K is the exercise price of the call option or put option. So in the case where S, the current market price, is greater than the contract price or the exercise price, then we will want to buy it, because that means we can make monies immediately out of it. Let's say we set the price to be 10, but right now this call has a market price of 15. Then we can buy it, we can exercise our right to buy it at 10, and then immediately in the market we can sell it for 15. So the amount of money we make is going to be S minus K, and that's where this comes from. And in the other case, where right now the market price is actually lower. So let's say the market price is $5, but inside this contract, I need to buy it for $10. Then you might as well not exercise it and be like, okay, well, why don't I buy it for $5? So in this case, we don't want to exercise this contract, which means this contract is worthless, and which is why this is 0 over here. But I want to bring in a little bit of complication into this equation, given that the assumption for all of this is we didn't really consider any of the other prices, or I forgot the name, sorry about that. But essentially, if you want to set a contract, you need to pay a fee. Well, yeah, the exercise fee for each of the option that you buy. So essentially, you do lose money. It's not like a 0 over here, but for the scope of this course, we don't really talk about the fee over here. So that's about that. And similarly for the put option, again, in reverse, if you want for selling, right? So if you can sell it for higher, then you want to sell it. If you can't sell it for higher, then you would not want to sell it. So it's just a reverse order. And over here, this is 2 of the results that has been indicated inside the lectures. So essentially talking about the same thing. So if at one stage the market price of the stock is 0, meaning that it's not worth any money, then in this case you would not want to buy anymore, right? You won't want to buy it for, let's say, $5 anymore. So in this case, the call option, your ability to buy for the preset price is going to be worthless because, well, there's no worth of the option anymore. And same thing with the put option, where you can sell it if it's worth 0. So if S is equal to 0, then that means you want to sell it because now you're making more money. And the price that you want to sell it for is just going to be the present value of the exercise price, K. So K is the exercise, and the present value is really just calculated by this exponential function over here. And that's what you have for the put option when the asset price is equal to 0. So hopefully that makes sense. And now following from that, we have put call parity. And I believe this is also covered inside topic 7, so I'll just briefly cover it again. Essentially, it's just talking about this formula or this equation over here. And sorry, there's a typo again. So to actually prevent the possibilities of arbitrage profit, we have to make C and P, the call option and the put option, satisfy this equation over here. And you can see that this is really what we just talked about previously when, where is it? Here. This is really just what we talked about previously. This is the present value of the asset price. Yeah, so this is the present value of the asset price. So we have to make sure that the present value of the asset price plus your call option is equal to the asset price plus your put option. So that's essentially what it's saying about. And here are the definitions. So that's put call parity. It's just a way to prevent arbitrage profit, in short, in very simple terms. So that's essentially all of the content that has been covered in lecture 10. I will be doing a question at the very end that combines all of these concepts with topic 11 as well. So we will look at that in a bit. So topic 11 is about PDEs and finite difference methods. So essentially this is just providing you with some methods, either explicit or implicit, to actually solve the Black-Scholes principle that we have covered just then. As you can see that the Black-Scholes principle seems pretty complicated, the PDE over here seems pretty complicated, and we didn't really do the derivation or how to actually solve out this formula, and that's what topic 11 in short is doing for you. It gives you some explicit and implicit methods to solve the things. So firstly, for the finite difference methods, we have in fact three different methods. One is the explicit method, second is the implicit method, and the third one is Crank-Nicolson's scheme, which is a very complicated way of solving the same thing. So yeah, let's start with the explicit method. So here's the equation or the final result that you can obtain from the method. Again, I didn't really give you any derivations of these. It's all inside the lecture slides. You can take a look. And more importantly, inside the next question, I will be going through bits of the derivation as part of the question as well. So just bear with me with that. And the alpha, beta, and gamma are just these complicated terms that you kind of have to know. So again, you could have really just dropped that down inside a cheat sheet to bring inside exam. And don't worry about these formulas. If they do ask you, they're most likely going to give it to you inside the question as well. So the next thing about the explicit method is talking about the stability of the method. And we know that for this scheme to actually be stable, we have to make this ratio over here, which is the ratio between the time and the asset price, to be smaller than a certain threshold. But this threshold, again, it's kind of human made. It doesn't really have a range or something, so you just have to look at a question and see. They probably will give you some guidance if they decide to ask this question during the exam. And the second method is implicit. So a contrast between explicit method and implicit method is just that explicit gives you the result straight away, so it gives you a solution straight away. Implicit methods, you have to do some calculation of linear systems or etc. to actually obtain the final solution. And you see that these two are kind of the same. Like the formula is, I think, oh yeah, it's the same. It's not the same, sorry. I thought I typed it wrong. But yeah, so you see that it really kind of is the same thing. Even with the alpha, beta, and gamma, they look pretty similar, just with some sign changes. But depending on what information is given, you might need to use one compared to the other to actually solve to the question. So again, for implicit methods, we have to solve a lot of linear systems, and the linear systems given over here, so this thing over here. And A, V, and B, they're all defined inside lectures. It's pretty complicated, so I didn't write it down. So if you want to take a look at this, go back to the lecture slides, and you should be able to find this. So lecture slides 11, slide 15. And what I want to emphasize on is A. So A is the coefficient matrix that gives you the alphas or whatever terms that's included inside here. And it has some properties. So A does have some properties that, in a sense, simplifies the calculation of the linear system. So it's tridiagonal, it's not symmetric, and it's not... I'm not going to try to pronounce that, but essentially remember this word is basically saying that you have a system that has column-wise the same elements. So let's say like maybe the diagonals are all A's and below this are all B's and all C's and stuff. So it's like the diagonals are the same elements is basically what this word is saying, but it's not that. And finally, it's independent of n. So remember, n is just how many intervals you want to separate it into for your prediction. So that's essentially what this is talking about. And again, for the stability, in contrast to explicit scheme, the implicit scheme is a lot more stable, and it doesn't really have a restriction to this ratio over here. Just a thing to keep in mind, really. And finally, we have the method 3, which looks a lot more complicated than the previous two. Again, in my memory, I haven't really seen this being asked in present years, in the following years. So who knows, there might be a chance that they decide to ask you on this. But essentially, again, they will give you the formula for this. The only difference with the scheme for the Crank-Nicholson is the definition of T. So the current step that we want to predict or that we want to calculate out inside the model. So we see that there's a different definition for all of these. We have T as either T plus 1 or just T or the gap, a fixed value. But over here, we're actually combining the current step and looking to future in the previous step to actually give us a model, which is given over here. So yeah, that's in short, very, very brief, what Crank-Nicolson scheme is doing. And why do we need such a complicated scheme when we have explicit and implicit already available to us? And the answer in short is about the accuracy. So we see that over here. The accuracy of the explicit and implicit schemes are the same, and Crank-Nicolson improves on the accuracy of the scheme. And we see that essentially this is what we have. So the order of approximation is over here, and this gives this is a equation that's I just copied down from the lecture slides that gives you kind of the order and accuracy of the schemes. And you see that from what you can see over here, the Crank-Nicolson model, I think this might be wrong, sorry, I might copy this wrong, but it improves on the order and accuracy. That's why it makes sense for this one to be a bit more complicated than the previous ones. So that's essentially about these schemes. Again, obviously having an intuitive understanding and knowing how to actually derive these are important, but inside exam, if you just want to get the exam done with, in a sense, all you have to know is the equations and what process are involved in coming up with these, and that goes into our Taylor expansion, that goes into the forward difference and central difference and stuff, which I will talk about inside the question over here. So now this is the final thing of my presentation, and this is just going to be a past paper question, and I will go through the 2020 T1 question 4, the entire question 4, that kind of encapsulates both topic 10 and 11 with the Wayner's process, or not really Wayner's process, sorry, with black scores and with change of variables and stuff. So let's take a look at the question first. So firstly, they gave you the black scores PDE, which is this equation over here, and these are the definition over here. And we assume that like the interest rate and the volatility are known positive constants, so yeah. And for this question, they are trying to price a put option. And in previous years, they have also asked about call option. Again, it's the same thing, but just shifting a few letters around. That's the difference. And yeah, that's just a definition of put option. Yeah, so firstly, they asked you to carefully explain what the initial conditions for these problems are, and I'll combine it with question II as well. So explain what are the boundary conditions for this problem are. So in short, initial conditions are the conditions that allows you to start the question, kind of in short, and the boundary conditions are what conditions do you have at the boundary values. So the boundary values include R from 0 to infinity and T from 0 to the expiry time. So it should be pretty simple. Firstly, the initial conditions is at expiration we have T equals to capital T, which is a constant or will be given, kind of. And we know that for WRT, which is defined by the question over here, where is it? Yeah, the value of the option. So be careful that they kind of changed the letters around. Above we used V, but now they're just using a different letter W, and R with the asset price. So remember, before we used S, but now it's just using R. But again, the same thing. So with the value of the option, is just equal to max 0 L minus R, and this is just really by the definition above that we talked about. So this line is just replicating, where is it? Yeah, that line. But, oh, sorry, this should be a P. My bad. Okay, but it's replicating this line over here, and I just wrote up the entire definition. So having this inside a cheat sheet will be a good idea as well. So yeah, so that's about I, pretty simple. For II, boundary conditions, again, we're just talking about what are the values at the boundary that we have defined. So remember, R has a boundary from 0 to infinity, and that's why we have these two over here. And that just goes down to substituting it into the formula. And again, this is already written inside the previous definitions as well. So just scroll up and you will find the definition there. So yeah, this, I don't think it's anything too complicated. And again, L might confuse you, but L is just a strike price, which we used K before. So it's just confusing letters, really. All right, so that's the first two parts. And with III, here is where the change of variables actually come in, where you want to change it to log or log moneyness in, to actually solve the PDE. So remember that I have highlighted above where the Black-Scholes is a log normal distribution, and this is where the change of variables actually come in. And here the time of expiry, they just use this Greek letter over here. So this is the definition by the question that's already all given. Firstly, we want to find expression for these three partial derivatives, which is what we have the change of variable for. So remember, inside the Black-Scholes, we have defined the value to be W, but now we want to change the variable of R and T into S and tau and have another set of expression to actually express it. So let's talk about this bit first with part A. Firstly, this is the first thing that we want to find, and we know that V by the question is just given by that, right? So we see that V, where is it? V is RT, and we know that R is this thing over here, T is that thing over there. And because we want to differentiate it in respect to tau, so that's why R really doesn't influence anything, because you see R is LE with this L and exponential of S, so it's independent of the time, and that's why I just wrote it as R as normal. And over here, that's just our chain rule. So pretty trivial to actually know. Chain rule would differentiate inside with respect to tau. Differentiating this gives you a negative sign only, and then we have W. So essentially, you don't really have to write this, but I put it on. So this is the expression. And the next one is a tiny bit more complicated, but really it's the same thing. So again, V is just representing this function over here. And because we are differentiating with respect to S, that's why we need to kind of write down the first one. So R, again, it's just that thing. And with the differentiation process, we see that we use the chain rule over here, where we have chained up the W and a tau using, oh, sorry, this shouldn't be a tau, this should be S. Yeah, so we kind of just chained it up. And the reason for this is because given that L exponential of S is a function with respect to R, so we kind of have to differentiate R and then differentiate R with respect to S again. So dW dr, that's we keep it there. And again, reiterating R is just that thing over there. We differentiate it. Pretty easy differentiation. It's exponential differentiation, so it doesn't change. And finally, remember, again, that thing over is just R, so we write it as a more simple way of expressing it. So am I going into too much detail? I don't know, but let's speed it up. We are nearly at the end. And secondly, we want the second derivative of V and S. So same thing. Second derivative of the expression above just means differentiating this thing again. That's what I wrote over here. And again, we use chain rule. So we bring out the R because we bring out the R because, again, R is really just this thing over here. And differentiating that thing gives you R. We've already covered that. And we have dW dr, which we kind of already did. So I'm not going to really go into detail for this one, but essentially over here, you split it apart using your product rule. That should be fairly easy to see. And after applying a product rule, you just differentiate as normal, and that will give you the final solution over here. So that's part A. Now part B, we want to show that the Black-Scholes principle in PDE in equation 1. So like, where is it? This long thing over here. This long thing over here is equivalent to equation 2 that's given over here. And you see that it's really just using all of the change of variables that we found in part A. So I didn't really write it down because it's really just, all right, put these results that we found in part A into the equation and over here, and then after some rearrangement, you will get this equation over here. So pretty simple. And C and D, we want to find initial conditions and the boundary conditions of the transformed problem. So remember, we have found initial and boundary conditions already. And again, that's just change of variables. And in fact, more simple because it doesn't deal with differentiation. So it's written over here. I'll quickly go through it. Again, the change of variable or the transformation is given over here. And we know that originally we have found this to be the initial condition. And remember, again, R is just given inside here, inside the transformation. So we take the L out because of linearity. That's the final answer. So simple algebra. This is given inside a question. This is given inside a question for the transformation. So when R is equal to 0, that really corresponds to when S is approaching negative infinity according to the definition given. And when R is approaching to infinity, it corresponds to infinity. Again, just algebra. So we apply the two conditions, boundary conditions above when R is equal to 0 and R is equal to infinity. So you see that it's over here. Yeah, so it's really just the same thing, but writing it in terms of the letters that they require over here. So we have S infinity, that's the same condition, negative infinity and infinity, which is 0. And note that we wrote tau instead of t minus t, because that's what we want inside the question. Remember, tau is just t minus t over here. So that's C and D, pretty simple. And finally, we have the last part, and I did not write down the question because it's pretty long, so I'm just going to put the question over here. So here's the question that we have. And yeah, so essentially this is relating to all of the topics that we covered in lecture 11 with, the V's, the central difference approximation, and also the explicit implicit scheme. So let's quickly skim through the question. This is the definition. We use this grid over here to do our approximation, where S-min and S-max is the upper and the lower bound. Oh, and I forgot to mention one thing. Inside this scheme over here, we actually have a kind of a condition. Remember before we talked about S being inside a range of 0 to infinity from a previous definition of Black-Scholes, but inside the finite different methods, it's pretty trivial from the name already that we can't really deal with infinity in a sense. That adds too much complication, and it messes around with like the accuracy and stability. So what we do instead is we say we find a value S that is sufficiently large to encapsulate the infinity. So instead of that, we will transform it into kind of like S0 and S max. And this X max is just going to be a constant value that we personally define that kind of caps the upper bound of the stock price or the asset price in a sense. So that's just one thing I want to quickly mention. And that's where this comes from. So S min to S max over here, and we have the expiration time T. And this is the definition. So the change in stock price is given by S max minus X min over M plus 1. M plus 1 is really just how apart do you want to separate the predictions. And again, this is just the same definition as what we have defined all the time. And this is the expression to denote the approximate solution. And the first part, they want you to use central difference approximation to find the partial derivatives of these two things. So as a revision, central difference approximation, I have stated the formula over here. And sorry, I'm going a little bit over time. Over here. So here are the definitions over here, the central difference approximation formula. We have the first order to calculate the first thing that we want, second order to calculate the second derivative. So we see that for the central difference approximation, we are talking about the current value plus, so we're looking one step into the future, which is here, and one step into the history, kind of like, so it's looking at essentially like this. So this is your t, and this is your t plus delta t, this is your t minus delta t, kind of thing. So let's look at these two things over here, and that's exactly why we have the thing divided by 2 delta t, because this is a delta t, this is a delta t. That makes a lot of sense, hopefully. And second order essentially is the same thing. It's really similar to the differentiation formula and derivation that we did in high school, in a sense, but like in more complicated terms. So we see now with these two formula, it's really just rewriting it in terms of the expression that's given, and you see that this is altering the n plus 1 and n minus 1. It's changing the Sn over here. The j is not changing, and the reason for that is because the definition. Oh, wait, the definition's over here. The reason is because of the definition over here, where we are altering the first thing over here. So I don't know if you can see it, but I can draw on this. Yeah, so we're altering this thing over here, where we go look one step into the future, one step into the history. So same thing over here, which is applying the formula. You see that this is n plus 1, this is n, and this is n minus 1. So we look at 3 stages of the current, previous, and the future. So that's with A. And B, again, it's really the same thing, but we're using forward difference approximation. And I have stated a formula over here as well. This is the formula, and it makes a lot of sense that because it's called forward, so we look one step into the future. And obviously there's something called backwards difference approximation, and it should be pretty trivial that backwards is just talking about ft minus ft minus delta t over there. This is backwards. So, but that's just something to make sense of. So again, applying the formula, but be very careful inside this case, because we are differentiating in respect to tau, not s anymore. So what we are actually changing, the delta is on the j's, because the j is the thing that changes tau, but above, because we're differentiating in respect to s, that's why we change the n. So that's just really putting the formula into restating the formula in terms of the question. And finally, the last page, we have CA and CB, so the last part of this question. Again, we want to use the finest different methods, which is the topic, exactly the topic 11, for computing the equation. And you can see that this is exactly what has been stated inside the definition slides for the approximation. And how do we actually do that? Firstly, we know from IRIB, which is what we have above, so here, from this Black-Scholes PDE again, just to reiterate, finite difference scheme is something to actually calculate or help us produce results for the Black-Scholes PDE. So with the formula above, all we have to do is to substitute these things above into the equation. So we see, let's highlight it, the dv d tau, this thingy, is just this thing over here, and this is this over here, and finally we have this, which is this over here. So you see that it's really just substitution, which is the reason why I didn't write it down, because it's a lot of writing. So the only thing to be careful of inside this case is really just copying the things, because it does get annoying, and make sure to not copy anything wrong. So yeah, that's it. So we substitute inside. Oh, actually, I wrote it down. Okay, so we substitute everything inside from above. We rearrange it to become this form over here. So it's really just algebra. We substitute, we do some like multiplications, rearranging, combining like terms. And after combining the like terms, whatever you have in front of this is going to be your alpha. So you just label it out really. So yeah, so that's basically with this part, it's just algebra. And finally, we have the final question. Again, they're talking about the initial and boundary conditions for this change of variable again, so this transformation. And again, because it's transformation, another typo, sorry about that. So this should be S subscript N. Okay, so essentially, we go back to what we have over here again, and you see it's exactly the same. So it's just really talking about exactly the same thing. This one and this one. Here, here, and here. So these three things. Yeah, so it should be pretty simple to see. All we are doing is, instead of writing S, which we have as the asset price, we talk about Sn, which is when we slice it up into pieces. That is defined by the question. So again, the slicing is given over here. So here are the slices. Sn. What is wrong with this? Yeah, but this is the slices over here. So yeah, and again, these follow the same thing. The slicing over here gives you for the tau as well, instead of just having the one time. And be very careful, the n+1 came from the definition as well. So the definition of the boundary for n is given by n+1 over here. So that's essentially this question over here, question 4. So yeah, that's basically the end of my session as well. Hopefully I gave you some insights or more details about how to approach these questions, and some more fundamental things about how to what will be covered inside exam. So if there are no questions, let's take a look. Yeah, seems like there are no questions. But if there are no questions, then this is basically it for the session. And yeah, good luck for your exam.